Welcome to Brain Buzz Podcast. We are a podcast that is dedicated to making research engaging, accessible, and fun to listen to. Each and every episode has a new researcher on, ranging from topics on casual sex to nonverbal behavior to today what we're talking about with Ben Davis Purcell is particle physics. So if you skipped grade 11 physics or it's been a couple decades since you took the class, this will be the episode for you. Before we jump in, I want to announce that we have launched a Patreon page. So if you want to make research accessible and science accessible to others, and you like what we're doing at this podcast, please do check out our Patreon page. You can go to our Facebook, our Twitter, or our Instagram page to find the URL for that. Depending on how much you love us, there are different tiers. The first tier allows you to have access to our Discord channel, which is going to have a lot of like-minded people that are interested in research and science, a lot of undergrads, graduate students, and just science lovers in general on there, and a lot more other awesome things. So please do check out our Patreon if you want to support us and the podcast. It helps us tremendously. If you're someone that likes to watch podcasts on YouTube while you're working or while you're at your computer, please do check us out at Brain Buzz Podcast on YouTube. We have recent episodes out and we're going to be publishing new episodes with video coming soon. So please do check that out. Anyways, that's enough from me. Enjoy the episode.
Friends, colleagues, and particulate masses, welcome to another episode of Brain Buzz. We are your hosts. I'm Kyle.
And I'm Drake.
And today we are joined by Carlton, PhD candidate in physics, and scientist working on the ATLAS experiment at the European Organization for Nuclear Research, better known as CERN, home of the Large Hadron Collider, Ben Davis Purcell. Ben, welcome to the program.
Thank you. Really excited to be here. Thanks for having me.
Yeah, absolutely. And Ben, you you convinced me over Twitter to have another physics episode that I swore I wouldn't do this quickly, but now we're a physics podcast, as it seems like. You have some really cool work, Ben, and you literally said you convinced me over messages on Twitter, and you did it in one long paragraph.
I was worried about that. I was hoping to not overwhelm you, but entice you at the same time. So I'm glad that was successful.
Yeah, no, you did it. You did it quite well. I mean, it didn't take too long. It was a good little chunk on Twitter DMs, but I love it. And honestly, you sold me right away. The work that you're doing is really, really cool. And I know nothing about it. Kyle knows nothing about it. But we've heard a lot about it in the news, and just in general, it's really a popular topic is particle physics and talking about this hadron collider. But we know nothing about it. So how about we start with what particle physics is?
Yeah. It's interesting how, for some reason, particle physics often ends up being the subject of science that gets highlighted in these news stories. But I guess that's just a good sign for the advertising of people in particle physics somehow.
Somehow you're like the darling. It's like you're the darling aspect, of, the darling part of physics. Like people really are fascinated by particle physics. You're the Hollywood celebrity division.
I mean, I guess astronomy too, to be fair, right? About planets and stars and everything too. But we won't talk about that.
Yeah. I'm talking about.
I'll bring my. You can hype me up, and I'll bring myself back down there. All right. So to answer your question, particle physics is the study of the smallest things that exist in the universe. So as small as you can think of, and hopefully even smaller, that is what we are studying. So the most common particle that we would be aware of, let's say on a day-to-day basis, is an electron. So most of us have heard of an electron before. The flow of electrons is the definition of electricity. So that's obviously completely vital in our day-to-day lives. And so the electron is a particle. And in fact, it is a fundamental particle, which means it cannot be broken down into any smaller constituents, at least as far as we know yet. So, but that is what particle physics is studying. These ideally, we look for fundamental particles, but just the smallest things that make up the universe.
So what other fundamental particles are there?
So we have what's known as the standard model of particle physics. So it's like one of these buzzwords maybe that often shows up in various articles. But really, what that means is these are the list of fundamental particles that we know describe everything that we, first of all, interact with in day-to-day life, and really everything that we understand in the world can be zoomed in and then therefore described by these fundamental particles. And so there are in total 12 fundamental particles that, let's say, do something or like move around and bounce into other particles to make things happen. And then there are 4 fundamental force-carrying particles. So you actually split particles into particles that feel forces and particles that transmit forces. And then each of those particles has a corresponding antiparticle. So when you actually sum it up, plus 1 particle that I'm leaving out, because it sort of is in its own category called the Higgs boson. So there are 17 particles, and then 16 of those have antiparticles.
Okay. And these antiparticles are the like villain to the superhero here. What are they? What's their purpose?
They are very simply, basically, the easiest way to think about them. Is the opposite charge of the particle. That's nothing crazy about them. But if a particle and an antiparticle meet in space, they will annihilate into pure energy.
Interesting. And what is pure energy? I don't know anything about physics here. This is going back to the Big Bang at this point. Like, what is pure energy?
Yeah, I mean, it sounds cool when you say it like pure energy, but but really, pure energy is a photon.
Okay.
And
I'm going to continue to make myself sound stupid here. What is a photon?
Excellent question. No, very good. Okay, so when we're talking about particle physics, to introduce it properly, you really have to talk about this force-fueling set of particles and force-transmitting set of particles. Now, there are 4 fundamental forces. Everything that happens in the world, well, in the universe, can be described by these one or some combination of these 4 fundamental forces. The one that we are most common with, or that matters the most in our day-to-day lives, is the electromagnetic force. The force, an example of a force-feeling particle of the electromagnetic force is the electron. The photon is the force-carrying particle of the electromagnetic force.
Yeah, I think that's coming together. That's coalescing for me.
Okay, yeah, it's much easier if we think about it as an example, as a more straightforward example. So if you were to like bang your fist on your desk or your computer or whatever is in front of you right now, why does your fist or hand or whatever not go through that table or pass through the computer?
Because I'm not strong enough. Is that what you're trying to say, Ben?
Yeah, that's it. That's particle physics is the study of one's inner strength. Yeah.
Okay, so
time at the gym recently. So.
Yeah, I won't take that personally, Ben. So the that is what you consider an example of electromagnetic force is the actual interaction between 2 like objects and like it's stopping more or less.
Yeah, exactly. If you boil it down to a force, which is the only reason why your hand does not pass through a desk, let's say, if you zoom in at the smallest scale that we can zoom into, it's because the electrons in your hand are repelling against the electrons in the desk, and so it just can't pass through. It is simply an electromagnetic force that is stopping your hand from passing through. And so then if you really zoom in, you can think of that electromagnetic force. It is, you have these electrons and these other electrons repelling each other. So electrons are negatively charged particles. Negative charges repel each other. And so you can think about it as like when 2 electrons get really close, then they repel, but how they're actually repelling is like they shoot out photons, or they shoot a photon at each other to transfer that energy and then repel. So the photon is like what is causing an electron to repel. You can think of like a photon smashing into another electron to shoot it away.
Right. Yeah, I'm thinking of like whenever you're, just getting introduced to physics at a young age, they get the magnets out and you see that the negative is literally, you can feel the negatives pushing against each other. And you feel that with like those simple magnets. And that's the case for any electromagnetic force. And it's just that you're looking at these very small, the smallest particles the smallest unit that we can look at, which is a particle.
Exactly.
So what happens when one particle, the smallest unit that you can look at, hits another particle? What happens to each particle?
Yeah, so we can actually really just think about it as like pool balls on a pool table, as an example. So it's really just like you're shooting a pool ball at another ball, and they collide at some angle, and then they both go off in some different direction based on the angle or based on how powerful you were when you're smashing the pool cue into the white ball, let's say. Mm-hmm. And so it's a similar thing with particles based on the amount of energy that a particle has, or maybe the amount of energy that you gave a particle to make it move. Then it'll bump into another particle and it'll shoot it off in one direction if the particle that you gave an initial energy boost to had more energy, or if it has less energy, maybe it'll recoil away. So, but really, I mean, in its most basic form, it's just like billiard balls smashing into each other.
Right. And does a force, how does a particle increase momentum, or how does it grow in force or power?
Yeah, so momentum, yeah. Well, you can certainly make a particle go faster and faster. Mm-hmm. That is what happens at CERN, which we will get to.
Yeah.
But one of the fundamental, properties of particles, a fundamental law in physics is that momentum is always conserved. So if you're going to increase the momentum of a particle, you have to be injecting energy into it through some means of giving something energy. Like you can think of like a battery, right? A battery injects energy into something, but that energy has to come from somewhere, comes from the chemical reactions inside of the battery.
Right. Okay, so you talked about electromagnetic force as one of the 4 forms of forces that you can look at in particle physics or in physics in general. What are the other 3, just so we know?
Yeah. Great question. So the other one that comes up most often in day-to-day life, in that everybody knows about it. It's the reason why we stay on Earth, and we can't jump from the surface of the Earth to the moon. What do you think? What do you think I'm talking about?
It may be gravity that you're talking about.
There we go. That's it. That is one of the 4 fundamental forces to go along with electromagnetism. Funnily enough, gravity is the force that at a fundamental particle level, we actually understand the least.
Really?
Like at our human scale, we understand gravity very well. But down at the particle scale, we have still a lot more to learn about gravity, interestingly. Okay. But anyways, the other 2, sorry.
Yeah.
And then the other 2 forces are really they don't affect us on our length scales, on the 1 meter, let's say, length scale, the size of a human. We have to zoom in to get a lot smaller before they become important, but then they are very important on smaller length scales. So they are called the strong nuclear force. The strong nuclear force is responsible for holding particles like protons together. So a proton it is not a fundamental particle. It is made of smaller constituents, but it is a particle with positive 1 electric charge, just like an electron is a particle with negative 1 electric charge. And so a proton is sort of like the fundamental building block for all molecules, everything that we interact with in day-to-day life. But a proton is made up of smaller particles called quarks, and the strong nuclear force holds these quarks together. So it's very important for everything to exist, but we don't actually measure it until we're looking at the length scales smaller than the size of a proton.
Right. Okay.
And
so
then
that's binding everything together, more or less.
Yes, exactly. Yeah.
Okay.
And then the fourth force is called the weak nuclear force, sort of corresponding to the strong nuclear force.
Yeah.
And that is responsible for nuclear decays. So the most common example of this is like a beta decay, or you can just think of like a simple radioactive decay. That's the common example that people may have heard of is like uranium decaying and giving off energy. That decay happens because of the weak nuclear force. Now, I mean, I don't want to give off the idea of like radioactivity and all this negativity associated with that, but that's a common example that comes up in media a lot, let's say.
Right. Yeah. Obviously, because of the implications associated with such.
Right.
Yeah. The weak nuclear force, is that kind of just like the opposite of the strong nuclear force? Because it's the strong nuclear force is holding them together, and the weak nuclear force, as you said, is the decay of those protons. Is that correct?
Yeah. So no. Like that is correct, but they are sort of named. The naming is more so strong and weak has to do with the length scales. So how zoomed in basically you need to be in order to feel that force or to measure anything about that force. And so really the strong means that it's a little bit bigger, a little bit more zoomed out than the weak nuclear force.
Okay. So Ben, is the work that you're doing specifically on electromagnetic force, or are you doing work on all types of forces?
Yeah. Great question. So I specifically work on an experiment called the Atlas experiment. And to just sort of, I guess we'll zoom in on that a little bit first, and then we'll back out and explain it a little bit more.
As you should with particle physics.
And we like zooming in and out of different scales, so it's perfect. So that experiment is what's known as a general purpose experiment or a general purpose detector, meaning it is not optimized for one specific force or not optimized to look for one specific particle, but instead the detector is built to measure everything possible, everything that we can hope to measure. The detector is built to be able to record all sorts of different particles and the corresponding forces and particles that transmit those forces like we are talking about, but it's not specifically zoomed in on any one of those forces or particles.
So it's sort of a scattershot approach, like, hey, we've got this facility, let's see what we can find kind of thing.
Yeah, exactly.
Cool. So with that in mind then, like, what does a typical experiment look like? Or what does the Atlas experiment do? Like, if somebody were to come and watch an experiment occur in the lab, what would that look like?
Yeah, so for this type of particle physics, we are looking at, like I said, all of the different particles that we possibly can, but we want to be able to create all of those particles, or at least have them appear in our detector somehow. And it turns out that the best way to do that is by smashing two particles that are made of more fundamental particles. So particles that are not fundamental. So specifically, I'm sort of beating around the bush of the word proton again. So what we do is smash two protons into each other at really, really high speeds. And then these protons collide and their inner constituents basically meld into each other, and you get this collision of a whole bunch of energy that then gets shot out around to the detector, which is surrounding this collision point, and then probabilistically over a large number of collisions, all the different particles that can be created are. So you're not going to create every particle every time two protons collide, but by making enough collisions and recording enough data, you will be able to see all particles that exist, and hopefully ones that we don't even know exist yet.
Okay, that's starting. I think I'm getting that. So when you say that, like, because I always think about science as being like this sort of replicability kind of thing, right? And so when you're saying, hey, we're smashing two protons together and we're hoping that it creates these particles, why aren't we getting the same particles every time?
Yeah, okay, so that's where quantum mechanics comes in.
Oh no, I'm sorry to have asked.
So yeah, without going deep into a quantum mechanics discussion, this is a great topic for a future podcast. I'm not a quantum mechanics expert, although I certainly have taken many courses on it. When you are at this level, this scale of the universe, right, down to the size of fundamental particles like electrons, the universe actually becomes probabilistic by nature. So, for example, if you are trying to say, when we are zoomed in really close, looking at an electron, if you wanted to say, well, I know that this electron is in this one exact spot, then what you are saying is that you know exactly where it is, but somehow at the same time, you also have no idea how fast it is going. So there is some probability that if an electron is in some given distance range, it is going to be moving in some given velocity range. So without going any further into that, basically there are probabilities of different particles being created so maybe, let's say, 1% of the time that two protons collide, we'll get out two electrons from that. Maybe 10% of the time that two protons collide, we'll get out a photon or two photons, like we were talking about before, to talk about some of the particles that we've mentioned. And some percentage of the time, the two protons will just sort of glance off of each other and not make any other particles and just sort of pass right by. So there's probability we can make everything that exists.
How fast are we talking about here? Like how quickly are those protons moving?
They are accelerated to 99.999999991% of the speed of light.
Holy shit, that's fast.
So how do you get them to move that fast then? Like how what's the equipment that you've been using in Geneva to do this? What does it do? How does it accelerate it that fast? And how large is it?
Yeah, awesome question. So this is where CERN and specifically the Large Hadron Collider come in, like you mentioned in the intro. So first of all, CERN itself is a massive particle physics lab that spans the border between Switzerland and France. The closest city, as you say, is Geneva. And the biggest, let's say, experimental apparatus at CERN is the Large Hadron Collider, which is basically a big tube, and by big, I mean 27 kilometers in circumference. Jesus, so a big, let's say, pipe underground, not so far underground, about 100 meters underground. And within that underground pipe are beams that have these protons circulating in them, and they go round and round and round until we make them crash into each other around or in the center of one of these experiments like mine.
Okay. 27 kilometer circumference is how big it is. How long is it? It sounds like it's circular. Is that correct?
Exactly. It is a circle. So yeah, Large Hadron Collider. Just to break down those words. Well, large because it's very it is large. Yeah,
That's self-evident. Yeah.
A hadron is a class of particles. So particle physicists really like making all these different categories to group particles in, and there's overlap depending on how you make the groupings. So anyways, a hadron is, for example, a proton. It is a particle that is made up of quarks. So like I was saying, protons are made up of quarks. So hadron is really just a fancy way of saying proton. And then collider, well, that means that they are smashed into each other.
Mm-hmm. Absolutely.
Okay.
That's really interesting. I had no clue it was circular. For some stupid reason in my head, I thought it was just like a roadway that went across the full like all of Switzerland, and that makes more sense that it's now circular, because the amount that you're going to have to make these, I mean, the speed that you're making them move, I'm sure that they're circling these the Hadron Collider multiple times, like.
Oh yeah, exactly. Yeah. So you've got it, and it's not at all stupid to think that it could be a straight line. I mean, there were many earlier experiments that were just straight line particle colliders, where you just smash two particles, they started opposite ends, and you just fire them at each other, and that's it. And and there will be more in the future. There is certainly benefits of that style of collider. Mm-hmm. But yeah, with a circular collider, that's where you can really get up to this nice high velocity. And in fact, it would be impossible if it was just this 127 kilometer ring. There is a series of increasingly larger rings that you have to continually accelerate your protons in before they get up to the max speed of the Large Hadron Collider itself. And then once you have your protons up to that max speed firing around the Large Hadron Collider, then that's where, exactly as you say, they can keep on going round and round and round until eventually they lose their energy and we're ready for the next injection of protons. So there are each proton is going around that entire 27 kilometer circumference 11,000 times each second.
That's an absurd number that is honestly like not comprehensible.
Yeah. Oh, it's not comprehensible for me either. Oh
yeah. Wow.
When you say that there's the detector in this huge, like, just area, like surface area within this, like, 27 kilometer circumference, how does it detect? How does it know where this collision is going to occur? Does it, or is it everything's kind of just on like a monitor? I'm trying to figure out how you actually pick up that, like I picture a microscope just like zooming in on these particles, but how does it detect it? How do you see these things?
Yeah, you're visualizing it in the right way. I like to describe the experiment as a really large microscope, because we are looking at really tiny objects. And so another way that you can visualize it is, like, let's say we have a bicycle wheel, like a tire, all right? And that you could, let's or even now simplify that to just a metal ring. And now let's break open that metal ring a little bit and take an onion and shove that metal ring right through the center of the onion, and then connect back the other sides. Now we've got a metal ring with an onion around that metal ring, with the ring going right through the center of the onion.
Right.
So by design, we make the protons collide right at the center of the onion, and the onion is our detector. That is our experiment.
Okay.
So by design, we make the protons collide there. So yeah, I mean, you are getting at a technicality that is important to point out. So really, there are two tubes in the Large Hadron Collider, one sending protons in one direction, the other sending protons in the other direction, and then they are made to collide right in the center of our experiment, along with the three others that are at different locations around the Large Hadron Collider.
Okay. Yeah.
Okay.
I mean, I never did I think that putting a ring in an onion would make sense for an analogy, but it did. That was a brilliant way of putting it. It makes a lot of sense.
Yeah. So is the speed important here? Like, do you have to go really fast to be able to create these particles, or? Or is it just fun to be like, yeah, look how fast I made this proton go?
Yeah. I mean, it's fun to say that you're going at 99.9999% of the speed of light. But yeah, if that wasn't necessary, then we wouldn't do it. It would make things much more difficult than it had to be done. It's so really. You can think about it in the famous Einstein equation E=mc squared. So what that means, that's like a common equation. Somehow that's like an equation that people seem to have heard of, that appears in movies a lot. And like, oh, Einstein equals mc squared. Well, what does that actually mean? It seems like really complicated. But what it is just simply saying that energy is equivalent to mass. So if we want to be able to create particles with larger mass in these collisions, we need to have larger energy. And so that is why you want to keep on increasing your energy, which means keep on making these protons go faster and faster in order to create more massive particles. And that again comes with this probabilistic nature of things. So the faster you are going, the more energy you put into your system, the higher probability that you will create higher mass particles more often. So that's everything that we do is based on some sort of theoretical prediction, and then we go and search for different energy regions based on those predictions. And so basically the world of particle physics has said we need to be looking in this larger mass range to better understand what we are looking to discover. For example, better understanding the force of gravity at this small scale. So yeah, we absolutely do need to be at this energy, and in fact, we always want to keep on going higher energy as well.
Yeah, and so that's exactly kind of leading to my next question, Ben. Is why are we spending so much time, energy, and money? Obviously, because I'm sure this project is very expensive to create something of that scale. Why is it so important, and what are the findings that are really, driving this research? What's the point in all this?
Yeah. Really, really good question. So we, first of all, for the cost of it, it is absolutely a really expensive experiment if you just look at the money involved. But because of that, we know that there are not going to be it is impossible for many different institutions or researchers around the world to each do their own experiments like this, right? It's not like there was so much money given to particle physics. It's more like all the particle physicists in the world interested in this all come to work together and pool all of their money for this one big set of experiments.
Right.
And so the fundamental reason is, well, we want to understand how the universe works, right? It is particle physics is fundamental research in that we are not like searching for a cure to something or trying to specifically solve one problem. It is about understanding how nature works at its tiniest possible level. And then we trust that with that knowledge that we gain, we will be able to use that knowledge to actually do things that are useful for everybody. And then the byproducts of what you obtain from that knowledge are basically the deliverables to society along the way. So like one quick example is like the internet. The World Wide Web would not exist if it were not for CERN. So the World Wide Web was created so that particle physicists could talk to each other and share their data more easily. This was created at CERN in the late 80s. So that's just like an example of a byproduct that comes from doing experiments like this.
Could you imagine just sitting around being like, you know what? We need to make this product that's going to make life easier. Let's just devote a bunch of time and effort to that. Then we'll come back to our other stuff. But like, let's deal with the like. That's insane to me. I mean, the history of the internet's kind of
Yeah.
just a wild story. But
But like, yeah, I mean, not it's you have to be committed to just learning and acquiring knowledge in order to be able to use that knowledge down the line, right? It's like when we discovered the electron, we didn't know that we'd be able to understand electricity and build computers down the line. Nobody would have like predicted modern laptops, for example, like we had when the electron was first discovered, like a little over 100 years ago. But because we studied the electron, or we searched for it, we found it, and then we studied it so well to really understand it, now we've been able to create these incredible computing devices, for example. And so the same can be said about other particles that we are understanding much better. So there's like down the line, maybe 100 years from now, this research has led to a form of communication, like basically nearly instant, nearly speed of light cross globe data transfer, let's say.
right.
Better than 4G is what you're saying.
Right. Yeah.
Yeah. Effectively, I guess what you're getting at is literally harnessing the power of these particles by understanding how they work and interact. We can then kind of harness that power and apply it in other contexts that have positive benefits for all of us.
Yeah, like these particles are literally the smallest things that make up everything, right? Like we can guarantee that everything that exists is made from some combination of these like 17 particles that I listed before. I mean, and actually, really, it's much fewer than that. In day-to-day life, most of the time, it's just like protons and electrons that matter for us.
Yeah.
But so by better understanding that, I mean, the possibilities are endless if we could increase our understanding of that. Excuse me, of that fundamental level.
That's brilliant. This is the first time I've ever actually understood what the Hadron Collider was all about, and learning more about particle physics is a unique perspective that, as you say, is the foundation for everything that exists, which is mind-boggling on its own. But you've done such an amazing job at making it simpler for me and for I assume our viewers to understand. Ben, what's a common myth that's associated with your research? I'm sure there's lots when it comes to particle physics. Do you have any popular myths or misconceptions?
Yeah, definitely. Yeah, I mean, I would say if you've never searched this sort of thing on YouTube before, don't go and just type in CERN Large Hadron Collider, because you'll find a whole bunch of different conspiracy theories about how it's going to cause the end of the world and all this stuff. Yeah. So make sure you're getting your information from nice science sources. Like two of my favorites are Physics Girl or Veritasium. Those are really good YouTube sources as an example. But yeah, so there was one big thing that went around the internet, and even you can still find, this is still a belief a lot of people have, is that the Large Hadron Collider, that CERN would create black holes that would suck in the entire Earth and cause the end of the world.
Absolutely.
I remember distinctly hearing about this, and I was going to ask you, so I'm glad that you brought this up.
Oh yeah, that's the most fun conspiracy theory, I think. So, and it is, of course, it is just that. It is a conspiracy theory. So, I mean, that's like coming from the idea that there's so much energy because we're accelerating particles to this almost the speed of light and smashing them into each other. That must be like a crazy amount of energy, right? Like don't even think about lasers, But if you actually think about it, like, okay, did you hear that clap that I just made?
Yeah.
All right, so that clap, there's more energy in that clap than the collisions from protons at the Large Hadron Collider. No joke. That's real. The thing about the Large Hadron Collider is the energy density. It's because you are colliding these protons, these particles, at such a small scale that the energy is very dense at that scale, but the total amount of energy is nothing, right? It's like actually it is about the same amount of energy as two mosquitoes buzzing. That's like the average collision energy of the LHC. So people were like, oh, we're going to be creating these black holes because there's all this energy and it's going to suck in everything. But I mean, we can very easily calculate that and show that it's impossible. So yeah, that would never happen.
Hey, quickly, you kind of mentioned sound here. Do the protons make a sound when they collide?
Yeah, good question. No, because there is these collisions. In order for them to happen, they have to be done in basically perfect vacuum. So all air is sucked out of the tubes where these collisions are happening, and so when there's no air, when there's no vacuum, sound doesn't exist. Sound is the collision of particles in the air. So
Right.
when there's no air, there's no sound.
Okay, that makes sense. Yeah, okay. That checks out in my little brain. All that kind of is coming together. We talked about this off the top. That people are fascinated enough about this sort of particle physics work that in many respects you're sort of the A-list celebrities of the scientific community, and yet there's just this. I mean, there's this incredible propensity to create myths and misconceptions and misconstrue what's happening at the collider. I guess it kind of comes with the territory of being the famous one, right?
Yeah, exactly. I guess because it's so well known, or I mean, it's a great tourist attraction, right? It's not like anybody can go and visit on a normal year in a normal given world scenario. It's open to the public, right? Anybody can book tours for the different experiments at CERN to just go look at the whole lab structure, right? It's not like we're hiding anything. There's nothing to hide, right? It's if you just go and look at CERN itself, you'll really just see a whole bunch of warehouses where people are working in their offices, and it's really doesn't look anything special outside of like the tourist area that has like actual old pieces of detectors that are really cool. So I think it's just done because it's this big thing that's in the media, and you slap the word physics on, and for some reason there's this connotation associated with that, and you're old. I mean, it propagated from all old science movies and that sort of thing, and then it's because of that it's so easy to just make some video and get clicks on YouTube or on the internet, and so really it's that's all it's about.
It's not Area 51 or anything.
No.
Like that.
Yeah,
You don't have armed guards here.
No.
Ben, you said it was super expensive, and I can imagine. And imagine you're not like it's not being run every day here. How often do experiments actually get run in the Hadron Collider?
Yeah, no, that's a great question. So there is a ton of work. In fact, I mean, most of the work associated with the Large Hadron Collider itself is figuring out how to accelerate these particles to these incredible high speeds. And that involves, well, a lot of magnets. And in fact, it involves a lot of what's called superconducting magnets, just to throw in another buzzword there. However, superconducting just means that the conduction, the transmission of electricity is so good that there is no resistance at all. So your electrical current will continue forever. That's what superconduction is. And in order to get superconductivity, you have to cool down magnets to, well, some of the coldest temperatures that we can make on Earth. So the magnets have to be cooled down to about 2 Kelvin, which is 2 degrees above absolute zero. As a reference point, open space, the vacuum of open space itself is 3 Kelvin, and the 0 degrees Celsius is 273 Kelvin.
Holy shit.
Okay, so cooling these magnets is really what takes the most energy, and the magnets have to be turned on and off in order to make them last longer, and there's other maintenance that has to go on. So all that is to say is that the actual Large Hadron Collider is firing protons and smashing them into each other about 2/3 of the year, and that goes on for about 2 or 3 years, and then the entire Large Hadron Collider is shut down for a year or two for basically all-out maintenance and upgrades, along with upgrades to the experiments themselves, and then you ramp things back up and do it all again, and then you cool them down, and then you ramp them up. And so it's like the entire life cycle of the Large Hadron Collider. It started taking data in about 2005, and it's going to continue running experiments until about 2035 or 2040.
Amazing.
Wow.
I for some stupid reason, I thought it was just like, you turn a microwave on whenever you want to do an experiment. And obviously it also adds into the myths and misconceptions, because no one knows that's not a part of it or hasn't seen it. They don't know what the hell's going on. And so that's really interesting that you're actually making things colder to speed that up. And how do you, I swear this is the last question I'm going to ask about it. How do you make it so cold?
Yeah, no, good question. The questions are great. So that is done by liquid gases, effectively. So obviously, if they're liquid gas, they're no longer gas, they're liquid. But so you supercool. The most common one that would happen that you use in like chemistry labs would be nitrogen. So that's like one way to start cooling things down, is by making liquid nitrogen. And then we also use liquid helium, liquid argon. So gaseous particles at room temperature. If you cool them down or force them to be confined to a smaller space and turn them liquid, you can basically flow them in tubes around the magnets to cool them down.
Awesome. Well, Ben, I just like to thank you so much for joining us on the program. It was a lot of fun to learn about all the wonderful work that's going on at CERN, and really just to get some insight into what it's all about, and for you, honestly, to endure our questions is quite kind of you. So thank you.
No, thank you very much for having me. This was awesome, and yeah, it's really nice to have like a visual representation for this kind of thing too. So I'd encourage listeners to, for example, look like at the Physics Girl YouTube channel, and she came last year for a full tour of CERN. Has some really nice videos of the facility, and also if you're just on YouTube and go to the official CERN YouTube channel, so that's just CERN on YouTube. That is the account name. Then they've got tons of really good videos of what actually it looks like when you're sending particles around each other through the Large Hadron Collider and colliding them. So really nice visual representations.
Fantastic. Ben, as well, if people want to keep in touch with you, how might they go about doing that?
Yeah, so you can follow me on Twitter. It's the only real social media I'm active on. So that's just my name, Ben Davis Purcell. All is one word and no hyphen, even though my last name is hyphenated. But yeah, you'll find me. I'm active in that. I only try and promote science or meet other scientists interested in outreach. And I was very hesitant to get involved in social media, but I mean, I never would have found out about your podcast if it wasn't for that. So now I've grown to appreciate the communal network that you can make, and I've met a ton of awesome people, scientists and non-scientists alike. So if you use it well, then Twitter can be really useful. So yeah, please feel free to connect and reach out and ask me any questions there too.
Great.
Absolutely. Yeah.
As always, you can find information and links to Ben's Twitter on brainbuzzpod.com. You can follow BrainBuzz on Spotify and Apple Podcasts. Subscribe to any newsletters, updates, content on brainbuzzpod.com. And of course, you can find us on Twitter, Instagram, and Facebook at BrainBuzzPod. Until next time, cheers.